We're going to talk more about growth and compounding, but now we're going to try it in reverse, just to shake things up a little bit. Last time we calculated that 500 growing at 5% per year for 15 years is going to be worth 1,039.46 at the end of the period. Now, if somebody asked you, okay, if 500 were invested in an interest rate of R for 15 years, and that's worth 1,039.46 at the end, what's the interest rate? You can figure that out. I mean, you just did it. The answer is obviously 5%. But if we hadn't just done the calculation, if we faced some general problem, how would I find the answer? I'd do a little mathematics. Set an equation that 500 times 1 plus r to the 15th power equals 1039.46 and solve for r. How do I solve for r? Remember your algebra. If I have some number x to the 15th power, how do I solve for x? I have to take the whole thing to the 1/15th power. You should remember that, doing that for lower powers. If you had x squared equals something, how do you solve it? You just take the square root. And remember, the square root is 1/2 power. You just need to remember your algebra. Alternately, we can ask the question, how to find z given that some amount z is invested at 5% for 15 years and it's worth 1039.46 at the end. That's even a little bit easier with some algebra. Z equals 1039.46 divided by parentheses 1 plus 0.05 all to the 15th power. The reason we're doing this in reverse is because we also often want to do discounting, which is discovering what is the value right now of some amount of money in the future. For now, we're going to ignore things like risk or inflation. We'll add those complications later. We start with the really simple case. How much money do I need to invest at some interest rate to get W dollars at some date in the future? From basic micro, the value of something is the opportunity cost. What do I have to give up in order to get something? In a simple case, if I can put $100 in the bank today at 3% interest rate and get $103 in 1 year, then the value of $103 in a year is going to be $100 right now, because that's how much money you have to give up right now in order to get $103 in the future. We call it discounting because the value goes down. $1 in the future is not worth $1 today. $1 in the future is worth less than $1 today because of opportunity cost, because interest rates. To put that equation into more mathy terms, after t years, z dollars initially becomes z times 1 plus r to the t power. How do you find the present value? W equals z times 1 plus r to the t power. Solve for z. Z is w divided by 1 plus r to the t. Rewrite that, w times 1 plus r to the minus t. Again, review a little bit about how exponents work. But this is called the present value, and it comes up again and again and again and again in finance application, because a lot of what Wall Street is doing is just saying, okay, somebody gets some money in the future, how much is that worth right now? That's discounting. You should pause the video and do these problems now. If R is 4%, what's the present value of $100 paid after 10 years? We know it'll be less than $100 because $100 to be paid in 10 years just ain't worth $100 today. I can put some money in the bank, get 4%, let that compound for 10 years. That's less than $100. What's the present value of $100 paid at the end of 50 years at an interest rate of 4%? What is the present value of $100 paid at the end of 100 years at 4%? You should be able to calculate these. You might note the answer will get smaller and smaller because of compounding. Even a small amount of money in the bank today, compounded over 100 years, will be worth a lot. So pause and do these calculations. You're back. Since the present value is going down and down as the time to compound goes up and up, we might suspect that it could converge to some value as time goes to infinity. Yep, like the last video, we're going to do this an infinite number of times again. What is the value of W dollars paid next year, and the year after, and the year after that, and the year after that, on and on and on forever? We can use our little mathematic brain, our algebraic brain, to know the way the exponents work. If I take some number that's bigger than 1 and square it, it gets even bigger. If I take it to the 10th power, it gets a lot bigger. If I take it to the 100th power, it gets a lot bigger, and so on. But that's in the denominator now. So it's 1 divided by some gigantic number, which is going to get closer and closer to 0. The sequence terms here, w over 1 plus r to the first, plus w over 1 plus r squared, plus w over 1 plus r cubed, plus w over 1 plus r, on and on and on to the t power. As t gets bigger and bigger, that term's going to get smaller and smaller. It's reasonable to think that it might converge to something. So we suppose it does converge to something. Call it x, and do a little bit of algebra to solve for x. Find x equals 1 over r. So if r is 5%, then x is 1 divided by 0.05. That's 20. If r is 4%, then 1 divided by 0.04 is 25. As r gets bigger, x is smaller, which, again, a common feature of discounting. There's another way of thinking about it. Perhaps it's a little more fun. Suppose I win the lottery. And we'll say I get 10 million because it makes the numbers easy. So it's not as big as Powerball. But, if I did win, how much can I take out? How much can I take out every year forever if I never touch the principal? Now, obviously, that depends on the interest rate. If the interest rate is 10%, then 10 million in the bank, I can take out $1 million a year and never touch the principal. If the interest rate is 5%, then I can only take out $500,000 a year. If the interest rate is 3%, then I can take out $300,000 a year. Yeah, all those are pretty nice. But, going back to the opportunity cost argument, what's the present value of, say, $300,000 paid each and every year if the interest rate is 3%? Well, that's 10 million. So these different viewpoints are going to give the same answer. Now, we've been using percentages, so let's do a quick review. Percent is a convenient way of writing a decimal. You just move the decimal point. 15% is 0.15. 99% is 0.99. 150% is 1.50. You see, we're just taking that decimal point and moving it over. So 1% is 0.01. 0.3 of 1% is 0.003. It's a very mechanical thing. We're just moving that decimal point. Later, we'll be talking about things like U.S. inflation data, where it's commonly reported as, for example, 0.2%, which means 0.002. We often also use percentages to compare two numbers. If A is half the size of B, then we'd say A is 50% of B. If A is a quarter the size of B, then that's 25%. If a variable is increasing, then there are a variety of ways of expressing it. If Z is 125% the size of Y, then that means Z is Y plus a 25% increase, or Z equals 1.25 multiplied times Y. Now, sometimes you got to look at it a little bit extra careful just to make sure you're not going fast and getting sloppy. At a lot of stores, they're putting stuff on sale. They count on the fact that people are fast and sloppy in their thinking. A store might advertise sale 50% off and then take an additional 25% off. Sounds good. But does that mean you get 75% off the regular price? Nope. That's the trick. It's right there in the words, but you got to read the words carefully to see the trick. Think about the extreme version. If they offered 50% off and then take another 50% off, would that mean they're giving it away for free? No. No, that just means you're getting it for a quarter of the price. They take half off, and then another half of the remaining half of a half is a quarter. They're offering a total of 75% off. Going back then, the offer to take 50% off and then another 25% off means you take half off at the beginning, and then you take a quarter of the remaining half, which is an eighth. In decimals, you'd get it at 37.5% of the original price. Similar question, what is 10% of 10%? You do not multiply 10 times 10 and find 100. Nope, don't work that way. You got to convert to decimals. So 0.1 times 0.1 equals 0.01. That's 1%. 10% of 10% is 1/10 of 1/10, so that's 1/100th or 1%. You just have to be careful. It's not that hard. Now, the final little bit to remember is exponents and logs. You've probably heard news items about some movie star or sports figure getting paid, and you hear phrases like they signed a 7-figure deal, which means that person got paid 7 digits worth of money, some amount between $1 million and $9,999,999. That's implicitly using a log scale, log-based 10. We could all measure our own salary in the same way. You and me and most people we know are getting 2 digits an hour. That's not as exciting. But, maybe somebody graduating gets initial salary in the high 5 digits, and after a few years of work gets 6 digits. That's nice. That's using a log scale implicitly, log base 10. Now, if you remember your math classes, we often use log base E because lots of reasons. The math works better, blah, 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 details. It's related to the fact that e to the r would have a constant percentage growth rate on a log scale, so it would give a line. That's one of the reasons in graphs we often show things on a log scale, so constant growth is going to be a line. But all this, if you've taken calculus, you know that already. Congratulations. If you haven't yet, you will.